Your refrigerator doesn't actually make cold, it moves heat. It's a subtle but profound difference. When you open your fridge, feeling that crisp chill, it's not because some tiny internal engine is churning out icy air. No, what's happening is a continuous, silent dance of physics, orchestrating the removal of warmth from inside, pushing it out into your kitchen. This elegant system, largely hidden from view, relies on a principle that might seem counterintuitive at first glance. We often think of cold as a thing, a substance, but in the world of physics, cold is simply the absence of heat. Your fridge, then, is a heat-transferring magician, and the magic truly begins with a special liquid called a refrigerant. For many decades, this was often a class of chemicals known as chlorofluorocarbons, or CFC, like Freon. But as we learned about their devastating impact on the ozone layer, the scientific community rallied to find safer alternatives. Today, refrigerants are often hydrofluorocarbons, or HFC, or even more environmentally friendly options like isobutane and R600A, which you might find in newer models. These substances have a unique property. They boil at very low temperatures, much lower than water. Imagine a liquid boiling not at 212 degrees Fahrenheit, but at temperatures well below freezing. This is the secret. Inside the walls of your fridge, there's a closed loop of tubing, a serpentine path, through which this refrigerant flows, constantly changing states. The journey starts in the evaporator coils, typically located inside the freezer compartment or behind the fridge lining. Here, the liquid refrigerant is exposed to the warmer air inside your fridge. Because it has such a low boiling point, it readily absorbs this heat. As it absorbs heat, the liquid refrigerant turns into a gas or vapor. Think of it like sweat evaporating from your skin. It takes heat with it, leaving you feeling cooler. This phase change from liquid to gas is where the initial cooling magic happens inside your fridge. Now we have a cold, low-pressure gas, rich with the heat it just absorbed from your food. But this gas needs to be moved. This is where the one truly moving part, the compressor, comes in. It's the heart of the refrigeration system, typically a black, humming cylinder at the back of your fridge. The compressor does exactly what its name suggests. It squeezes the refrigerant gas, increasing its pressure and, crucially, its temperature. This superheated, high-pressure gas then flows out of the compressor and into the next stage of its journey. From the compressor, the hot, high-pressure gas moves to the condenser coils. These are the black coils you might see on the back of older fridges or hidden in the side walls of newer, sleeker models. Here, the gas is hotter than the ambient air in your kitchen. Because it's hotter, heat naturally flows from the refrigerant gas into the cooler kitchen air. As it sheds this heat, the gas cools down and, still under high pressure, condenses back into a liquid. This is the point where the heat your fridge removed from your food is released into your home. Now we have a high-pressure, room-temperature liquid refrigerant. It's ready to absorb more heat, but first, its pressure needs to be dramatically reduced. This happens in the expansion valve, or capillary tube, a tiny, narrow tube that restricts the flow. As the liquid refrigerant passes through this restriction, its pressure drops suddenly. This rapid depressurization causes it to flash evaporate, partially turning back into a gas and becoming extremely cold. Think of it like a spray can. When you release the pressure, the can gets cold. This super cold, low-pressure liquid gas mixture then flows back into the evaporator coils inside the fridge, ready to absorb more heat from your food and start the cycle all over again. It's a continuous, closed loop, a perpetual motion of heat transfer. So while the compressor is the only truly active mechanical part, the vast majority of the cooling process, the absorption and release of heat, is a marvel of passive physics. It's the inherent properties of the refrigerant, its ability to change states with temperature and pressure, that does the heavy lifting. This elegant dance of evaporation and condensation, compression and expansion, has been refined over decades. Early refrigerators, or iceboxes, relied on blocks of ice, which absorbed heat as they melted. A much simpler, but also much less efficient, form of heat transfer. The first domestic refrigerators using mechanical compression appeared in the early 20th century, but they were often dangerous, using toxic refrigerants like sulfur dioxide or methyl chloride. Imagine that, a ticking time bomb in your kitchen. It wasn't until the 1920s and 30s, with the advent of safer refrigerants like Freon, that refrigerators became common household appliances. Suddenly, fresh food storage was revolutionized, reducing waste and improving public health. Beyond the basic vapor compression cycle, some refrigerators use slightly different methods. Absorption refrigerators, for instance, often found in RVs or off-grid homes, use a heat source like a gas flame to drive the cycle rather than a compressor. These systems often use ammonia as the refrigerant and water as the absorbent, with hydrogen gas helping to maintain the correct pressure. It's a fascinating alternative, demonstrating how the core principle of heat transfer can be achieved through different means. Then there's thermoelectric cooling, which uses the Peltier effect, passing an electric current through two dissimilar materials to create a temperature difference. You might find this in small portable coolers, but it's not efficient enough for large home refrigerators yet. So the next time you reach for a cold drink, take a moment to appreciate the invisible ballet of science happening behind that door. It's a testament to human ingenuity, transforming simple physics into an indispensable part of modern life. It's a reminder that even the most mundane objects in our homes hold layers of fascinating complexity, waiting to be explored. A world of hidden science, just a glance away. Uncover more surprising science hiding in plain sight by subscribing to our channel.